Steel teeth slam shut in the dark with the force of a collapsing gate, and somewhere inside the noise a man is screaming for his hand. Not far above him, cables whine under impossible strain. Wet stone shudders. A wall of earth, blasted open and stripped raw, hangs over the work like a wound. Steam rolls across the cut in white clouds. Grease runs black through the mud. Iron links, each heavier than a man's torso, drag across shattered rock and broken timber. Then the giant moves again. It does not walk. It heaves. A bucket the size of a room bites into the mountain face and rips away another load of stone, clay, and gravel as if the ground itself were soft enough to tear apart by hand. Entire slopes vanish in its jaws. Tracks buckle beneath its weight. Men disappear beside its gears. It swings, dumps, returns, and swings again, always the same motion, always indifferent, reducing ridges, embankments, and ancient hills into measured loads for dams, roads, foundations, aqueducts, tunnels, and cities not yet born. Around it, workers live in a world of crushed fingers, split boots, dust-choked lungs, and whistle blasts before dawn. They feed the machine with coal, water, rivets, cable, and flesh. They tighten bolts on shaking platforms above drop-offs deep enough to bury locomotives. They stand beneath swinging loads that can erase a body without pausing the shift. The giant makes concrete possible at a scale the old world could never imagine. It clears the cuts, lifts the aggregate, carves the channels, tears open the quarry, and prepares the ground on which modern civilization will pour its permanent weight. It is called progress when the mountain falls. It is called efficiency when the timetable shortens. It is called necessity when the hand is gone. And for decades, this forgotten industrial giant stood between the raw earth and the concrete world, remaking both with the same iron appetite. The paradox begins with a machine built to make the modern world safer, stronger, and more permanent than anything that came before it. Concrete promised endurance. It resisted rot, fire, and weather. It could carry bridges, hold back rivers, anchor towers, and turn unstable ground into fixed geometry. It became the material of dams, seawalls, factories, highways, power stations, apartment blocks, and foundations buried so deeply beneath cities that no pedestrian would ever know they were there. It allowed engineers to imagine a civilization not of timber and brick, but of mass, pressure, and permanence. Yet before concrete could be poured, mixed, transported, and set into the forms that defined the 20th century, the earth itself had to be broken open on a scale older tools could not survive. That work fell to the industrial giant. It was not glamorous. It left no polished monument carrying its own name. It stood upstream from the visible triumph, in quarries, cuts, gravel pits, dam sites, rail corridors, harbor expansions, and foundation excavations. Its purpose was brutal preparation. It tore aggregate from rock. It removed overburden. It carved channels through ridges. It lifted spoil away from trench lines and basin walls. It made level ground where none existed, and in doing so, it turned geology into schedule. This is the contradiction at the center of its history. The machine helped build a civilization of order through methods that were violent, unstable, and frequently lethal. The same steel giant that enabled cleaner water systems, stronger public works, and flood control could also shear fingers in exposed gears, snap cables under tension, collapse embankments, and bury crews in seconds. It gave engineers mastery over scale while stripping workers of any illusion that progress was humane. Its power was measured in cubic yards, cable diameter, boom length, boiler pressure, and daily output. Its cost was measured differently: crushed hands, broken spines, amputations, cave-ins, widowhood, and names entered into payroll ledgers for the last time. So the central question is not simply what this machine built. It is what kind of world required such a machine in the first place, and why the foundations of modern civilization were prepared by an iron system so dangerous that the men closest to it often paid for permanence with parts of their own bodies. Before the giant arrived, the crisis was already visible in the shape of the industrial age itself. The 19th century had built rapidly, but not always deeply. Cities expanded with astonishing speed on foundations that were often shallow, improvised, or dependent on older materials that could not bear the demands of the new century. Timber piles rotted. Masonry cracked under vibration. Roads dissolved into mud under freight loads their builders had never imagined. Rivers flooded urban districts with regularity. Rail corridors required cuts through stubborn terrain that hand crews could spend months attacking with picks, black powder, wheelbarrows, and animal teams. Ports silted up. Canals demanded widening. Reservoirs had to be dug, lined, and defended. And everywhere industry grew, concrete emerged as the answer, not because it was elegant, but because it was massive, cheap in volume, and increasingly adaptable. The problem was scale. Concrete is not born in the form of a bridge pier or dam face. It begins as extraction. Sand, gravel, crushed stone, water, lime, cement, and steel reinforcement all depend on prior systems of removal, transport, grading, and placement. Before the first form board could be braced, someone had to clear the site. Before a power station could rise, entire hillsides had to be cut back, unstable soils hauled away, and foundation pits excavated to bearing strata. Before a river could be disciplined by a dam, millions of cubic yards of earth and fractured rock had to be shifted under impossible deadlines. The age of concrete therefore required an age of excavation, and excavation at the old human pace was too slow for what states, rail companies, utilities, and urban planners now demanded. This pressure intensified between the 1880s and the 1930s, when industrial nations entered an era of territorial hardening. Harbors were deepened for larger ships. Rail and road networks pushed through mountain corridors. Flood control projects followed disaster after disaster. Massive civic works promised water security, hydroelectric power, sewage systems, retaining walls, subway lines, bridge abutments, and poured foundations for factories that would operate day and night. Population growth magnified everything. In the United States alone, urban populations exploded in the decades around 1900, and every new neighborhood, warehouse district, rail terminal, grain elevator, and municipal works complex required one thing before construction could begin: transformed ground. Hand labor remained essential, but it was no longer sufficient. Tens of thousands of workers still swung hammers and loaded spoil, yet the old methods had become a bottleneck inside a civilization that measured success by throughput. Contractors bid against time. Public agencies tied money to milestones. Delays on excavation could halt an entire chain of dependent trades: masons, carpenters, steel crews, concrete gangs, pipe fitters, and rail suppliers. Rain could ruin weeks of progress. A stubborn layer of rock could destroy a budget. A collapsing cut wall could kill men and force redesign. The industrial century demanded not just stronger materials, but machines capable of attacking the earth with repetitive, organized violence. This was the deeper crisis. Modern civilization wanted permanence, but it had inherited landscapes, labor systems, and construction methods unequal to its ambition. It needed bigger foundations, faster quarrying, deeper cuts, wider basins, heavier lifting, and standardized movement of spoil and aggregate. It needed machines that could turn a mountain into schedule, a pit into a ledger, and terrain itself into an industrial input. The forgotten giant rose to answer that demand. It belonged to the family of heavy excavating machines: steam shovels, cable excavators, draglines, stripping shovels, and giant material handling systems whose forms varied by task but whose logic was the same. They multiplied force. They extended reach. They mechanized the bite, the lift, the swing, and the dump. They reduced the earth into units that could be counted, priced, and accelerated. Around them, the concrete age became possible. But the same crisis that created these machines also shaped the world in which they operated: thin margins, unstable sites, exhausted crews, improvised safety, and managers determined to keep the work moving. The machine was not introduced into calm conditions. It was born into pressure, scarcity, competition, and terrain that resisted every promise made about controlling it. That is why its history cannot be told as a simple triumph of invention. It emerged because industrial society had cornered itself. It wanted larger dams, straighter roads, harder ports, deeper foundations, and cities built to endure fire, flood, and time. Yet to achieve that permanence, it first had to unleash machines powerful enough to deform entire landscapes, and place human bodies close enough to those machines that every shift became a wager between production and survival. The first versions of the giant did not arrive all at once. They emerged from a chain of industrial compromises, each one trying to solve the same problem with greater force, longer reach, and less dependence on raw muscle. In canals, rail cuts, harbor works, and open excavation, engineers had already learned a harsh lesson: hand crews could begin a transformation, but only machines could sustain one at the scale the new century required. The old sequence of men with shovels, wagons, horses, derricks, and blasting powder could still break ground, yet it could not keep pace with projects measured in hundreds of thousands or millions of cubic yards. The gap between ambition and available labor created the opening through which the great excavating machine entered history. Steam made the first decisive leap possible. Portable boilers and engines had already changed milling, pumping, hauling, and manufacturing. Once that power could be mounted on frames, connected to winches, chains, dipper handles, swinging platforms, and later cable systems, excavation ceased to be merely an extension of the arm. It became a cycle. Dig. Lift. Swing. Dump. Return. Repeated thousands of times. The power stroke no longer belonged to a single man. It belonged to a machine whose appetite depended on fire, water, and maintenance rather than breath. In the late 19th century, the steam shovel became the most recognizable form of this transformation. Early models were crude by later standards, but their effect was revolutionary. Mounted on rail cars or heavy underframes, equipped with boom, dipper, and bucket, they could attack embankments, quarry faces, and cuts with a force no gang of laborers could match. One machine with a skilled crew could do the work of scores of men under favorable conditions. On railroad projects, that difference changed bidding, schedules, and route selection. Terrain once considered expensive became merely difficult. Difficult ground became profitable if attacked with enough iron. As cities hardened and public works expanded, the family grew. Contractors needed machines not only for frontal digging but for longer reaches, wider spoil removal, loading from below grade, and work in unstable or waterlogged conditions. Draglines answered some of these needs by allowing buckets to be thrown out and drawn back, scraping material toward the machine from a distance. Clamshells handled vertical digging and bulk material. Giant cable excavators extended reach over pits and cuts where fixed geometry machines struggled. Stripping shovels evolved for mining and overburden removal at scales that made earlier excavators look almost domestic. The result was not a single invention but an industrial lineage, a growing class of giants designed to tear open the earth so other systems could follow. Their rise followed the largest projects of the age. Railroads through mountain corridors needed vast cuts, fills, and tunnels. Canal and harbor works demanded dredging, rock removal, and embankment shaping. Urban expansion required foundation pits for warehouses, stations, civic buildings, and later towers. Dams and reservoirs consumed entire valleys, not just with concrete but with access roads, diversion channels, aggregate plants, spillway excavations, and quarry systems feeding the poor. Mining operations stripped hillsides and overburden in quantities that would have bankrupted hand methods. Every such project rewarded machines that could convert geology into a production cycle. This was also the period when the machine's image became mythic. Contractors posed beside buckets taller than a man. Trade journals printed output figures like trophies, cubic yards per day, boom lengths, bucket capacities, fuel consumption, operating radius, cost per yard removed. Industrial exhibitions and technical catalogs treated these machines as proof that modern engineering had escaped the scale limits of the pre-mechanical world. They were not merely tools. They were arguments. Arguments that the earth could be reorganized by schedule. Arguments that delay was now a technical failure rather than a natural condition. Arguments that industry no longer had to negotiate with terrain, only overpower it. Yet the rise of the giant was never purely mechanical. It depended on logistics dense enough to support its bulk. A steam excavator or cable giant was not dropped onto a site and set loose. It needed transport, track or stable footing, water supply, fuel delivery, machine shops, spare parts, rigging, signal systems, and crews trained, often imperfectly, in operation and repair. Roads had to be strengthened for its weight. Temporary rails might be laid just to reposition it. Boilers needed feeding. Gears needed lubrication. Cables had to be inspected, reeved, tightened, and replaced. Bucket teeth wore down against stone. Pins elongated. Rivets loosened under vibration. Each increase in scale expanded the web of supporting labor around the machine. And still the pressure for larger models continued. The 20th century rewarded size because size lowered the unit cost of moving earth, at least on paper. A bucket that held several cubic yards could replace countless hand motions. A boom with greater reach reduced repositioning time. A heavier chassis stabilized larger loads. A machine that could swing farther and dump directly into rail cars, hoppers, spoil banks, or crushers compressed whole sequences of labor into fewer cycles. Output became the language that justified risk. If one machine could move in a day what older crews might move in a week, then almost every contractor, state agency, and industrial operator was driven toward greater mechanization. Concrete amplified that drive. Mass concrete works demanded aggregate in astonishing quantities. Dams, retaining walls, lock systems, bridge abutments, piers, culverts, flood channels, tunnels, and civic foundations consumed sand, gravel, and crushed stone by the trainload. Quarries had to be opened and enlarged. Access cuts widened. Waste removed. Stockpiles built. Feed systems supplied. Excavating giants therefore became invisible authors of the concrete age. Their names rarely appeared on monuments, but without them, the permanent geometries of the modern world could not have been established at speed. By the 1910s, 1920s, and 1930s, these machines were no longer novelties. They were expected presences at the edge of transformation. Their silhouettes rose above timber camps, strip mines, canal cuts, aggregate pits, urban excavations, and dam sites like moving pieces of industrial architecture. Some ran on steam, others increasingly on electricity or internal combustion, but the governing principle remained constant: amplify force, organize motion, dominate scale. The machine became larger because the projects became larger. The projects became larger because governments and corporations now imagined landscapes as solvable engineering problems. And each success fed the next ambition. But industrial rise always concealed a bargain. The giant saved time, reduced certain forms of labor, and enabled construction previously considered impossible. It also concentrated danger. What had once been dispersed across many men and many small tools was now focused into a few machines whose failures were correspondingly immense. A broken handle could maim one worker. A snapped hoist cable could kill 5. A collapsing spoil bank under a giant excavator could erase a crew, damage the machine, halt a project, and bankrupt a contractor in a single afternoon. The greater the machine's power, the narrower the margin for error. That tension was already present in its ascent. Even in the celebratory language of engineers and contractors, one hears the undertone of strain: foundations must be improved, cut stabilized, operators trained, rigging secured, maintenance disciplined. The industrial giant rose because it was necessary. It stayed because it was profitable. It became legendary because it seemed to solve the problem of scale. But all the while, inside its boilers, under its tracks, across its swinging radius, and along its exposed drive systems, another history was accumulating, one of close calls, amputations, structural failures, and men learning too late that a machine built to move mountains had no reason to spare a hand. To understand why this machine became indispensable, it is necessary to look past its legend and into its working anatomy. The forgotten giant was not powerful in the abstract. Its power came from a disciplined sequence of parts, each one transmitting force through heat, pressure, weight, leverage, and repeated motion. Whether it appeared as a steam shovel mounted on rails, a cable excavator on heavy tracks, or a giant dragline stretched over a quarry or cut, the machine followed the same industrial logic: convert stored energy into a controlled bite against the earth, then repeat that bite until landscape became material flow. At the center was the power plant. In steam-driven models, the boiler was the machine's furnace heart, a steel vessel fed by coal, water, and constant attention. Firemen shoveled fuel into the firebox, draft carried heat through tubes, and pressure built until it could drive pistons or engines connected to drums, winches, gears, and hoisting systems. Boiler pressure was not merely a technical specification. It governed rhythm. Low pressure slowed the cycle, weakened the lift, and invited delays. Excess pressure threatened rupture, a catastrophic release capable of shredding plate, timber, and flesh. Gauges, injectors, valves, and feedwater systems had to function with precision, but on many sites they operated in dust, cold, vibration, poor light, and the exhausting tempo of long shifts. The machine's strength therefore began with fire discipline. From the power plant, motion traveled into drums and transmission systems. Hoist drums lifted loaded buckets. Crowd mechanisms drove the dipper or bucket into the face. Swing gears rotated the upper structure. Return lines pulled the empty working end back into position. On cable machines, steel wire rope became the machine's nervous system, carrying force across sheaves and boom tips to a bucket that could be thrown, dragged, raised, and dumped through carefully timed operations. On shovel-type machines, the dipper handle and boom formed a brutal armature, one part guiding penetration, another bearing load, both under strain as bucket teeth bit into compacted soil, blasted rock, gravel banks, or clay. Bucket design mattered because the machine's relationship to the earth was mechanical, not symbolic. Teeth had to penetrate. Side walls had to contain. Capacity had to balance with stability. A bucket too small wasted fuel and labor, a bucket too large could overload hoist systems, twist booms, or stall the cycle in resistant ground. Engineers and operators therefore matched bucket size to material. Loose sand behaved differently from wet clay. Broken rock differed from shale, overburden, or frozen earth. In quarries supplying aggregate for concrete, the machine often worked in partnership with blasting teams. Explosives fractured the formation, the giant then loaded the broken mass into cars, crushers, or spoil banks. Without proper fragmentation, the bucket could glance, jam, or strike with enough shock to damage pins, crack members, or throw dangerous vibration through the frame. The boom itself was a statement of engineering compromise. Longer booms increased reach, allowing the machine to work deeper pits, broader cuts, and higher spoil banks without constant repositioning. But length magnified stress. Every extra foot increased bending moments, altered swing behavior, and changed how load forces moved through the structure. Lattice booms helped reduce weight while preserving strength, but they introduced countless joints, pins, and members vulnerable to fatigue, corrosion, poor repair, or impact damage. Under ideal conditions, the boom extended the machine's authority over space. Under poor conditions, it became a long lever amplifying every error. Beneath the upper works lay the problem of support. Some early giants moved on rails, which gave stable travel paths on prepared lines and made them efficient for railroad cuts and repeated loading operations. Others used crawlers or massive underframes better suited to rough ground. But no excavating giant was stronger than the surface beneath it. A machine weighing tens or even hundreds of tons could settle unevenly, tilt on bad fill, sink in saturated ground, or destabilize when working too close to an unsupported edge. Bearing pressure, track width, cribbing, timber mats, and ground preparation were not secondary matters. They were survival calculations. A machine designed to dominate the earth could be undone by mud, voids, slippage, or a bank undermined by its own excavation. The operating cycle looked simple to distant observers. In practice, it was an orchestration of timing. The bucket entered the material. The machine crowded or dragged. The load came free. Hoist engaged. Swing initiated. The loaded bucket crossed open air, often over men, cars, or uneven terrain. At the proper point, the operator tripped the load into a spoil bank, hopper, or waiting rail car. Then the empty bucket returned. Each motion had to be smooth enough to preserve momentum but measured enough to prevent shock loading. Jerky operations damaged equipment. Premature dumping spilled rock where crews might be standing. Overswing could strike structures, cars, or signal lines. Delayed swing reversal wasted seconds repeated hundreds of times per shift. The industrial giant therefore rewarded operators with judgment measured in fractions of time and feel transmitted through levers, pedals, brake bands, engine note, cable tension, and the visible response of the machine. That apparent mastery concealed layers of vulnerable detail. Brakes had to hold. Clutches had to engage cleanly. Pins needed lubrication. Bearings heated under sustained load. Gear teeth war against one another with the slow brutality of metal under pressure. Steam lines leaked. Riveted joints loosened. Cable strands broke one wire at a time before failing all at once. Bucket lips wore thin. Track links cracked. Boilers scaled internally if feedwater was poor. Dust invaded everything. Winter made lubricant stiff and steel brittle. Summer heat exhausted crews and expanded tolerances. Rain turned approaches into traps. Fine aggregate worked into moving parts like a grinding compound. Even a well-built machine depended on a culture of inspection rarely as consistent as technical manuals assumed. And yet when all of it functioned together, the giant achieved something close to industrial sorcery. Hillsides receded. Foundation pits deepened. Quarry benches advanced. Diversion channels opened. Spoil trains filled in a continuous rhythm. The machine turned terrain into volume, volume into transport, and transport into the raw precondition for concrete. A dam required aggregate, the giant opened the quarry. A bridge required abutments, the giant carved the footing. A sewer system required trenches and cut stone, the giant stripped the overburden and loaded the spoil. A city required firm ground beneath towers, roads, retaining walls, powerhouses, and waterworks, the giant made the invisible first incision. This is why the machine seemed larger than itself. It was never just one excavator, shovel, dragline, or cable system. It was a conversion device between geology and civilization. Its engineering united heat, steel, and repeated motion in service of permanence. But because that permanence depended on so many stressed components acting in sequence under terrible conditions, every successful cycle carried within it the possibility of failure. The very brilliance of the machine was that it concentrated force. The very danger of the machine was the same. The hidden flaw was never a single defect. It was structural. It lived in the collision between immense mechanical force and the unstable, improvised conditions in which that force was expected to operate every day. On paper, the giant could be described with confidence. Rated lifting capacity. Boiler pressure. Bucket volume. Swing radius. Ground bearing assumptions. Safe angles. Maintenance intervals. Cable life. But the paper world ended at the edge of the site. Beyond that point lay rain-soaked cuts, rushed assembly, exhausted men, shifting spoil banks, bad visibility, poor signaling, uneven blasting, and supervisors under pressure to keep output high enough to protect the budget. The machine itself might be engineered with rigor. The environment around it often was not. Its first danger came from exposed motion. Unlike later enclosed industrial systems, many of these giants left their violence in the open. Gears turned where men climbed. Drums revolved beside walkways slick with mud or grease. Brake linkages, crowd chains, sprockets, swing circles, cable runs, and hoist lines all moved in plain reach. A glove, sleeve, bootlace, or bare hand could enter the wrong space for a fraction of a second and be taken with mechanical finality. The machine did not hesitate. It converted entanglement into amputation faster than any coworker could react. Then there was the problem of tension. Steel cable gave the giant its reach and flexibility, but it also stored danger invisibly. A hoist line under load could look calm until a damaged strand failed, load shifted, and the rope snapped back with enough force to cut through wood, flesh, or bone. Boom pendants and support lines bore stress that accumulated over time through wear, corrosion, misalignment, and shock loading. One cracked socket or poorly seated pin could transfer strain elsewhere in the system until failure arrived not where men expected it, but where inspection had been hurried or skipped. Ground itself was another hidden enemy. The machine existed to overpower terrain, yet it relied on that same terrain for stability. A cut wall undercut too aggressively could slump without warning. Saturated soil beneath a crawler or rail bed could settle unevenly. Fresh fill placed to support travel might conceal voids. Spoil banks could appear firm until vibration loosened them. When a giant machine shifted unexpectedly, every load path changed with it. A boom that had been within margin could become overloaded. A bucket swing could widen. A rail-mounted machine could lean enough to throw the next cycle off balance. Collapse rarely began as spectacle. It often started as a few inches of movement no one had time to interpret correctly. Steam added another layer of peril. Boilers demanded disciplined water levels, clean feed systems, reliable gauges, and operators willing to slow work when conditions deteriorated. Industrial reality rewarded the opposite instinct. Delay was expensive. Low water, scale buildup, sticking valves, weak riveted seams, and poor firing practice all created the conditions for rupture. Boiler explosions on heavy equipment were less common than everyday crushing injuries, but when they occurred, the violence was total. Plate fragments became projectiles. Scalding steam filled enclosed spaces. Fire spread through timber decking, oil waste, and nearby structures. Men were not merely injured. They were torn, burned, and erased. The machine's scale also produced a psychological flaw: distance disguised risk. To managers, investors, and even some engineers, the giant represented efficiency in bulk figures and daily output reports. But danger was always local. It existed at the pin being hammered in with tired hands, at the brake band adjusted in poor light, at the cable splice judged good enough for one more shift, at the signal misunderstood through steam and dust, at the labor standing one pace too close to the swing path because the work had become familiar. Industrial routine made catastrophe ordinary right until the instant it was not. This is what made the giant structurally dangerous. It required precision inside environments built on haste. It demanded disciplined maintenance inside systems organized around production. It concentrated force where labor remained cheap, replaceable, and often insufficiently trained. The flaw was not that the machine was badly conceived. The flaw was that the machine's true operating conditions were always harsher, dirtier, faster, and more humanly fragile than the design ever admitted. Before the whistle, there was darkness. Men woke in bunkhouses, boarding shacks, rail cars converted into sleeping quarters, canvas camps, and rented rooms near pits, quarries, and construction corridors where the ground never stopped trembling. In winter, the air bit through blankets before dawn. In summer, the rooms held yesterday's heat and the smell of damp clothes, coal smoke, old leather, and bodies too exhausted to care. Boots were stiff with dried mud. Hands were swollen before the shift began. Some men wrapped old cloth around split palms. Others worked with fingers already scarred smooth where nails had been crushed and grown back wrong. By first light they were moving toward the machine, carrying dinner pails, tools, tobacco, and the silence of people conserving strength. The giant was usually visible before it was fully heard. A silhouette against fog, steam, or quarry dust. A boom above the tree line. A bucket hanging still for the last moment before the day's motion began. Then the sound came in layers, the hiss of steam, the clank of links, the metallic cough of gearing taking load, the deep impact of bucket teeth entering rock, the rattle of spoil into cars, the shouted signals half lost in distance. No worker had to be told where power was concentrated. The machine announced it. Life around it sorted men by proximity to risk. At one level stood the operator, elevated in status but not protected from consequence. He needed judgment, timing, and the confidence to move tonnage within feet of men, rail cars, embankments, crusher mouths, and timbered platforms. A poor operator could destroy output. A reckless one could kill without touching the ground. Nearby worked the fireman or oiler, feeding fuel, watching pressure, greasing bearings, wiping rods, checking valves, and enduring heat that made the machine's interior feel like a furnace wagon. Rigging men handled lines, hooks, shackles, and cable runs. Ground crews cleared spoil, set cars, moved timber mats, checked track, drove wedges, signaled swing paths, and entered precisely those spaces the machine could erase in one mistimed motion. The labor was relentless because the machine's appetite reorganized human time. When the giant stopped, everything behind it slowed, loading, hauling, blasting, grading, crushing, pouring, and payroll itself. So men worked to keep it moving. Grease was applied in haste. Brake adjustments were made between cycles. Pins were drifted into alignment with hammers while steam drifted over the platform. Repairs that should have taken hours were forced into minutes because management counted idle equipment like bleeding money. A worker might spend half a day knee-deep in slurry, another half on iron lattice or crossties slick with rain, then be told to stay after dark because the next section had to be cleared before concrete gangs arrived. Pay reflected the hierarchy of danger imperfectly. Skilled operators might earn more stable wages, but laborers, riggers, and maintenance hands often absorbed the most immediate bodily risk for less money and less authority. Immigrants, migrants, black laborers, and the poorest local workers were frequently given the dirtiest and most exposed tasks, especially in periods and places where labor systems were openly unequal. If a man protested, he could be replaced. If he was injured, compensation was uncertain, slow, or absent. Many sites existed in the era before modern safeguards, when the boundary between accident and accepted loss was deliberately vague. Meals were short and inadequate. Water could be warm, dirty, or far from the active face. Dust-coated food. Coal smoke mixed with the smell of wet rope, hot metal, and exploded powder. In aggregate pits and quarries, fine particles entered the lungs with every breath. In muddy excavations, boots remained soaked for entire shifts, inviting rot, chills, and infections that were not dramatic enough to be recorded but serious enough to shorten lives. Men learned to read danger in small signs, a strange vibration in the swing, a delayed brake response, a frayed section of cable, a bank face shedding pebbles, a boiler sound that was no longer ordinary. Much of survival depended not on formal instruction but on the transmitted instincts of older workers, where not to stand, when to distrust a load, how to watch the machine without staring at it directly. And yet there was pride. Brutal, defensive, sometimes bitter pride, but real. These men knew they were doing work beyond the scale of ordinary labor. They could look at a cut through a ridge, a widened harbor, a foundation pit, a quarry bench, or the first poured section of a dam and say with accuracy that none of it existed before the machine and the men around it arrived. The world above them would later see only finished concrete, clean retaining walls, paved roads, hydroelectric stations, bridge piers, and dry foundations beneath public buildings. The workers knew what had been beneath those achievements: shale, muck, unstable clay, standing water, fractured rock, and the daily possibility that one slip, one swing, one snapped line, or one hand in the wrong place would make the job final. By night, the body carried the evidence home. Hands cramped even in sleep. Ears rang with mechanical rhythm. Dust came out of the nose black or gray. Men spoke about injuries in the practical grammar of work: lost fingertips, smashed feet, a shoulder gone bad, a man buried last month, another burned near the boiler, another knocked from the bank and not seen again until the spoil was shifted. Grief had little ceremony on industrial sites. The shift changed. The machine continued. New men arrived. Old men learned to move more carefully or disappeared from payroll. This was worker life in the shadow of the giant, not heroic in the ornamental sense, but defined by endurance inside a system that required bodies to remain close to industrial force while pretending that skill alone could neutralize it. The machine promised mastery over Earth. The workers lived with the truth that such mastery was purchased one shift at a time, through fatigue, improvisation, and a daily intimacy with injury that the finished concrete world would never remember. The climax rarely began with a dramatic warning. On most sites it started as a deviation so small that only the men closest to the machine could feel it. A cable sounded wrong. A bank face trembled after the last blast. The loaded bucket swung wider than expected over the spoil track. Brake response came a fraction too late. One rail settled. One timber mat cracked. One boiler gauge drifted. One foreman, under pressure from schedule, ordered the work to continue because the weather would turn by nightfall and the concrete gangs were already waiting downstream. That was how industrial catastrophe often entered the record, not as a single event descending from nowhere, but as the final moment in a long chain of tolerated strain. Imagine the sight at midshift. The giant is working the edge of a deep excavation feeding aggregate and fill for a major concrete works project, perhaps a dam, perhaps a flood wall, perhaps the foundations of a harbor expansion. Days of rain have softened the upper bank, but the cut must advance. Spoil cars are lined up below. Men with shovels and bars are clearing the loading line between cycles. The operator can see part of the face, not all of it. Steam drifts across the boom. Dust from earlier blasting clings to the wet surfaces like paste. The machine takes another bite. The load comes free heavier than expected. A skilled operator feels that difference instantly, in the drag, in the pitch of the engine, in the hesitation before swing. He compensates. Hoist engages. The bucket rises. The upper works begin to turn. Then the near track settles into softened ground by only a few inches, just enough to change the geometry of the lift. The loaded bucket, now slightly out of line, swings wider over the men below. Someone shouts. A signal is misread. One laborer runs in the wrong direction because there is no safe direction once the machine has lost its rhythm. The bucket strikes a spoil car hard enough to throw rock and shattered timber outward. A coupling snaps. One man goes down beneath falling aggregate. Another is hit by flying iron. The operator slams the brake, but shock loading travels up through the rigging into a cable already weakened by wear and poor inspection. The line parts with the sound of a rifle volley magnified through steel. Its recoil tears across the platform, smashing railings and cutting through a signalman before whipping into the mud. Now the bank moves. What had been loosened by rain, blasting, and undercutting finally releases. Earth does not collapse gracefully. It liquefies, then surges. Clay, rock, broken roots, and water pour into the working area, taking crossties, shovels, men, and one section of track with it. The giant lists toward the slide. For an instant its boom hangs at a wrong angle against the sky, as if even this machine has been surprised. Then the lower structure sinks on one side. Steam erupts from ruptured lines. A boiler fitting fails. Scalding vapor floods the cab and machinery deck. Men on the ground cannot see who is trapped and who has jumped clear. They only hear metal grinding against itself while the whole apparatus settles into the collapsing margin it helped create. This is the industrial confrontation in its purest form: machine, terrain, labor, and schedule colliding at once. In some cases the climax was a cave-in. In others a boiler burst. Elsewhere a crane overturn, a snapped hoist, a dropped bucket, an ignited fuel line, a strike born from repeated injuries and ignored warnings. The exact form changed, but the structure remained. Workers absorbed danger until one event made the invisible bargain public. A body crushed by gears might be recorded as misfortune. 5 dead under a spoil slide became inquiry. Repeated amputations around exposed mechanisms became grievance. A foreman forcing men under an unstable bank could turn private resentment into collective refusal. The machine's violence, tolerated in fragments, became politically visible only when concentrated into spectacle. And workers did resist. Not always through formal unions, though where unions existed they often seized upon such incidents as proof that output targets were being purchased with blood. Resistance could be immediate and local. Crews refusing to enter the swing radius until damaged rigging was replaced. Firemen declining to raise steam in a boiler they no longer trusted. Laborers walking off after a burial because the dead man's brother was told to take his place before the soil had settled over the coffin. Skilled operators, difficult to replace, sometimes exercised the only leverage they possessed by slowing work under the cover of caution or mechanical complaint. In the heavily industrial decades of the early 20th century, such refusals mattered. A halted giant did not merely stop one task. It choked a sequence of dependent operations and exposed the fragility of the whole project schedule. When official investigations followed disaster, their language was often clinical. Contributing factors: soil instability, mechanical fatigue, inadequate drainage, improper signaling, deferred maintenance, failure to observe safe clearance. But beneath that vocabulary lay a more brutal truth. Everyone on such sites understood the hazard long before the report named it. The men knew which cable should have been replaced. They knew the bank was wet, the brake uncertain, the visibility poor, the repairs hurried, the boiler temperamental, the foreman impatient. Disaster did not reveal unknown danger. It revealed known danger that had been normalized. And when the dead were counted, the work often resumed with astonishing speed. Bent rail was replaced. A damaged bucket was repaired or swapped. New men were hired. Output was recalculated. The giant, if salvageable, returned to motion over the same wounded ground. Concrete schedules did not mourn for long. Rivers still had to be dammed. Foundations still had to be cleared. Aggregate still had to be loaded. This was the darkest triumph of the machine age, even catastrophe could be folded back into production. The consequences spread far beyond the site itself. When one of these giants failed, it did not merely injure workers or delay a contract. It exposed the architecture of an entire industrial system built on compressed time, unequal risk, and the quiet assumption that ground, machine, and labor would obey if enough force were applied. At the most immediate level, disaster altered engineering practice. Contractors and public agencies were forced, sometimes reluctantly, to take soil conditions, drainage, slope stability, and machine footing more seriously. Ground that had once been treated as a temporary inconvenience became a formal object of calculation. Better cribbing, wider crawler support, improved track preparation, and more disciplined benching of cuts did not emerge from abstract wisdom. They were learned through collapse. The same was true of rigging inspection, boiler supervision, signal protocols, and clearance rules around moving equipment. Every regulation written in cleaner language had usually been drafted in the shadow of some earlier violence. But the consequences were not evenly distributed. Owners and agencies often absorbed disaster as cost. They measured delay, repair, insurance, and litigation. Workers measured absence. A missing wage packet. A hand that no longer closed. A spine that could not return to lifting. A widow negotiating compensation against an employer who treated injury as a matter of unfortunate circumstance rather than structural design. Industrial law in many places evolved slowly, and even where compensation systems improved, they rarely restored what the machine had taken. The bargain remained unequal, the concrete world accumulated public value, while the injuries required to build it remained private burdens carried inside households, boarding rooms, and labor communities. There were broader political effects as well. Repeated injuries around heavy excavation, quarrying, and material handling machinery fed demands for union representation, inspection regimes, and stricter employer liability. In some regions, reformers used industrial accidents to argue that modern engineering required modern governance, that large machines could no longer be left to the customs of the frontier contractor or the improvisations of local bosses. Safety began, unevenly, to shift from personal caution toward systemic obligation. Not because industry became humane, but because the scale of mechanized harm made older excuses harder to sustain. Yet even as regulation increased, the giant's deeper legacy hid itself in plain sight. The machine vanished behind what it enabled. Concrete walls stood where unstable earth had once collapsed. Highways crossed cut rock. Reservoirs filled valleys. Bridges held. City foundations remained invisible beneath streets, towers, train sheds, warehouses, treatment plants, and apartment blocks. The public saw permanence and called it progress. Very few saw the prior stage in which mountains had been bitten apart, spoil hauled away, banks stabilized after burial, and men fed the machine until the site was ready for the celebrated material to arrive. That invisibility may be the machine's final historical victory. It made the concrete world seem natural, as though modern civilization had simply appeared in poured form. But beneath nearly every durable surface lies the older violence of preparation, the excavation, stripping, loading, grading, and removal that made permanence possible. The forgotten giant did not merely build projects. It built the conditions under which 20th-century infrastructure could be imagined at all. And so its true consequence is double. It enlarged human power over landscape, and it revealed how easily industrial society could hide the human cost of that enlargement beneath the very structures it called civilization. In the end, the giant was forgotten precisely because it succeeded. Its name disappeared behind dams, roads, foundations, flood walls, quarries, piers, tunnels, and stations that seemed to belong to concrete alone. But concrete was never the first act. Before the pour, before the formwork, before the clean lines of modern permanence, there was the machine that tore open the earth and the worker who stood too close to its gears. That is the buried truth beneath modern civilization. Permanence was prepared by violence. The ground under cities, bridges, reservoirs, and power plants did not simply yield. It was bitten loose, lifted away, and paid for in flesh. The forgotten industrial giant moved mountains so the modern world could stand still.